Okay, so we are going to make a start, guys. So today we are exploring the fundamental theorem of calculus. Fancy name for not that bad ordeal, really. In the last lesson, we looked at the definite integral, where we evaluated the integral to a particular value, and we saw that the definite integral was simply the area under the curve. And I posted a video that explained why in about 20 minutes. It was a 20-minute long video or something, wasn't it? But you don't need to know the why, you just need to know how to use it. There's two things you mainly need to know, really. You need to know that the definite integral gives you the area under a curve. And secondly, you need to know how to calculate that definite integral. On Friday's lesson, you were given the value of the definite integral for particular ranges of functions and asked to work out what the areas would be with more complicated expressions, or you were given a graph and then you could just use your geometric formulas of area of a triangle or trapezium or rectangle or whatever in order to calculate the definite integral. However, you could imagine there is a whole bunch of functions out there where that wouldn't really suit us. So in today's lesson, we'll explore that through what we call the fundamental theorem of calculus. I'm going to zoom out now so you can see the whole lot. And I did write this down on the whiteboard on Friday, but we never looked at it specifically. So there it is there. If we have an integral on an interval from A to B of a function with respect to x, then the evaluation of that definite integral is given by, this is new notation, these square brackets. I actually didn't use square brackets when I grew up. I use this notation. I'm just going to write it, but then erase it, because just in case you come across it, you might see this notation, a single vertical bar, and then the interval endpoints there. So if you see that, it means the same thing. I'm just saying because I know that you might do some study online and you might come across and you go, what? But the textbook uses the square brackets notation, which is why I'm using it. Blip, 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 blip. So you find the antiderivative, f of x, and then you evaluate it by substituting in the interval points and subtracting them. That's it. That's it in English. So f of b minus f of a. So there's the conditions there, where f of x, big F of x, is the antiderivative of little f of x, and the function is continuous on that interval. That's what a less than or equal to x less than or equal to b means. It means the interval between a and b. What does continuous mean? And I shouldn't be asking you if you don't know the answer to that. You should be asking me. Harrison, you want to have a crack at it? Yeah, doesn't stop. If you imagine it as a line, the line doesn't stop. Anyone want to add colour to that one, that description? Yeah, any real value of x, do you mean, between the two interval, has a corresponding f or y, yeah. So good. So between the two of you, that nails it. Graphically, it's a continuous line with no breaks in it. Algebraically, we're saying that for every value between a and b, there is a corresponding value for f. Okay, that's what makes it continuous. All right. Any questions? Just to give a bit of a non-example, if I drew like, I'll erase this as well. If I drew like a function, this function here, like the hyperbola function, like that, and I said, what is the integral between here and here? The answer would be, can't do it, because it's not continuous over that interval. But I could work out the integral between here and here, because it is continuous between those 2 points. Is that okay? So if there are gaps, you can't work it out. I mean, you can. sort of. You just have to break your integral down into the different the different parts and then integrate it from there. Alrighty, so that's basically the fundamental theorem. What I'd like to do now is I'd like to go through an example and go from there, if that's okay. So do you mind if I zoom up? Is that okay if I do that? Just so I can make it a bit bigger for everyone to see. Cool. Sorry, Ashley? Yeah, when I zoom up, it's probably easier to see, isn't it? Is that okay? So the first thing we do is integrate it, or find the antiderivative. I was using a bit of a thicker pen. I've changed it to a thinner pen now, so it should be not so squishy anymore. So if I integrate 3x squared, you might be able to do that by inspection and know that's just x cubed. And just to follow the rule through, it's like 3 times 1/3 x to the power of 3 between 3 and -2, which equals x cubed. And there is absolutely no drama with you going straight to x cubed. I don't think it's a particularly necessary step, that first one. I just put it there so you can see how I did it. But again, if you can see by inspection that, oh, if I make that x cubed, you know, the derivative of x cubed is 3x squared. So if you know that already, you can just do that. It's all good. And then you substitute in the points. So you go, that's equal to 3 cubed minus -2 cubed, which is equal to 27. 3 3s are 9, 3s are 27. And -2 cubed, just be careful. Remember, when you raise a negative number to an odd power, the answer is negative. If you raise it to an even power, the answer is even. Sorry, is positive. So -2 times -2 is positive 4 times -2 is -8. So we're subtracting -8. So we're adding 8. Is that okay? So 27 plus 8, which is equal to 35. Any questions about that? You evaluating that on your calculator, Harrison?
Yeah, so I'm just checking.
No, did you get? You should have got the same answer. I hope you did. Yep. So now we're freed from our calculator, though, aren't we? Which is good, because you don't want to have to reach to your graphics calculator for routine calculations. Just slows you down in the end, and if you make typos on your calculator, it's sort of a bummer as well. So these are what I would call routine calculations once you've well practiced enough. Does anyone have any questions before I move on to some harder examples and stuff? No? You're a good crowd. You can come again. What about C? You'll notice that when I anti-differentiated 3x squared, I didn't go 3x squared plus C. I just said 3x squared. I could have gone 3x squared plus 1 or 3x squared plus 2 or 3x squared minus 15, but I didn't. I just used the basic function where C is equal to 0. In other words, I'm not adding anything. The reason why is kind of it's unnecessary. Is more so, not that you can't, but it's unnecessary. I'll show you what I mean. I'll just keep that zoomed out, but I'll just zoom in on my own screen. So let's just say I'll use the same function again. So from 3 down to -2, I am integrating 3x squared with respect to x. And this time, when I find the antiderivative, I'm going to say that's equal to x cubed plus 17.1. Just to be cray-cray. All right, so 17.1. I know this is true. This is a true antiderivative, because if I derive that, the 17.1 disappears and x cubed goes to 3x squared. So I know that's a true antiderivative of it. But when I apply the next step of finding the definite integral, let's have a look. We would have 3 cubed plus 17.1 minus -2 cubed plus 17.1, which equals 3 cubed, I'm deliberately not evaluating much yet, plus 17.1 minus -2 cubed, and minusing an addition is the same as subtracting, so it's minus 17.1. Okay, so that constant value has been added, but then because I'm subtracting f of a, big F of a, then I end up subtracting that constant. And so the constant disappears. And I just chose a random 17.1. I could have chosen pi, I could have chosen 2/3, I could have chosen negative 1 billion. Doesn't matter, because when I add it and then subtract it, it cancels each other out. So rather than make our lives hard, so since I can be choosy about what c is when I work out the definite integral, I choose 0 because it's easy. It's the easiest, because effectively means I can just ignore it. Does that kind of make sense? So antiderivatives, for a definite integral, you can choose the most basic antiderivative, which is when c is equal to 0. Questions? Shall we look at a harder example then? The next two examples, well, I'm going to go one example and give you some try time, and then I'll do a more complicated example after that, after you've had some try time. But I'm just using examples from the textbook. So they are written in the textbook for you. I might solve them slightly differently. I'm not sure. I haven't really looked at it. But I just use the examples from the textbook because then I know they work out fairly well. And we can check our answers. So I'll just zoom up on that because there's nothing else really to see on that screen as well. So you might as well have the full screen to see. We've got an integral on the interval 1, 3. Okay, so going from 1 all the way up to 3. And the function is 4x squared times x minus 1 dx. Now, it looks complicated, but it's not that bad, really. The first thing to notice is that 4x squared and x minus 1, they bear no relation to each other. One isn't the derivative of the other. I can't use a substitution technique or anything like that. It's just what it is. So I'm going to have to work on it from there. We also know this is not true. Just like it isn't true for derivatives, we can't use something like this. In other words, we can't just find the integral of the parts. That doesn't work for multiplication or division. It only works for addition and subtraction. So we can't use that. So we're kind of stuffed until we manipulate it a little bit. In this case, it's really straightforward. We simply expand it because then we'll have a bunch of terms added and subtracted together. So 4x squared times x is 4x cubed. And 4x squared times 1 is 4x squared. And so I've got that. That I can derive. Now, if you want to be fancy schmancy, you can do things like split it up. So you've got the integral of 4x cubed minus the integral of 4x squared. And then you can then take the 4 outside the integral and then just integrate x cubed and stuff like that. So there's a few things you can do, a few rules you can use in order to do it. But I reckon that function by itself is relatively simple enough just to integrate as it stands there. So that's what I'm going to do. So my next step is to do the basic integration. So the integral or the antiderivative of 4x cubed is x to the power of 4. Is that okay without spelling it out? I'll spell it out. I won't write it though. So if I increase the power by 1 here, it becomes x to the power of 4, which means I need to put a quarter here, and 4 times a quarter is just 1. So there's no coefficient. Yep. So the antiderivative, you add 1 to the power, and then you multiply it by 1 over that new power. Okay, thanks, Harrison. And then 4x squared is minus, okay, well, if I increase this to 3, then I'm basically going to have 4 over 3 x cubed. Is that okay? So the over 3 comes from the new power, and the 4 because it was there already. Goodly doodlies. And then I've got the interval being 3 to 1. That looks a bit dodgy, that 3. I'll do that one. Zip, zip, zip. Okay. So we'll evaluate that now. I'm just wondering whether I should just factorize it first or something, but I can't be bothered. I think it's okay if we just, the numbers aren't that hard. So I'll just go, that's equal to 3 to the power of 4 minus 4/3 times 3 cubed minus 1 to the power of 4 minus 4/3 times 1 cubed. Is that okay? And the rest is just a numerical thing. I hope you're okay with it. 3 to the power of 4 is what? 3 to the 9, 9 to 81. And here I have a fraction of 3 here, so that'll cancel out with one of the 3's here, leaving me with 3 squared. That's 9. And 9 4s are, I believe, at last count, 36. So I've got 81 minus 36 minus 1. And then minus becomes a plus, and 4/3 times 1 to the power of 3 is just 4/3. So there's a 3 here and a 3 cubed here. So I cancelled the 3. Yeah, I cancelled the 3 out there to leave me with 3 squared, and then 9 4s are 36. Do you want me to write that in so I can see it? So 3 goes into like that, and 3 squared is 9. And then it's just a final calculation, right? So let's just do it. 81 minus 30, oh gosh, 81 minus 36 is 45, isn't it? Yay, 45 minus 1 is, I reckon I can do that, 44. So it's 44 and a third. Oops, 44 and 4/3, I forgot the 4 there. 45 and a third, because 4/3 is 1 and a third. I think that's right, off the top of my head. And that's it, that's your answer, 45 and a third. What do you reckon? All good? Ready for some practice? So these first set of problems there, exercise 9I, page 310. First of all, I did example 11C. There's an A and a B as well, you could imagine. So you can have a look at a couple of more examples if you're just keen to see it in action there. Exercise 9I on page 310. I've given you a sort of like a jump in point if you're feeling confident of question 4. But otherwise, start from question 1. It's all good practice for you. And I can probably give you, what's the time? Stupid smartwatch. Yeah, I can probably give you about 20 minutes practice on that, I reckon. Maybe 15 and see how we go with that. Yeah, and they don't use any special techniques in exercise 9I, so pretty much just the power rule. And then when we return in about 15, maybe 20 minutes time, we'll go through a more tricksy example. So here we go. We're looking at example 12D on page 311. You don't need to have it open because I've got it there on the screen anyway. I'll zoom up so we can just focus on that problem and nothing else. Example 12D looks horrible, but it is not too bad. But there's a couple of little tricks you need to pay attention to. So we're asked to find the integral on the interval 0 to 1 of 2x squared plus 1 all cubed multiplied by 4x with respect to x. Now, at first blush, that's a very doable problem, but laborious and long. Could you imagine? You could use Pascal's triangle or binomial theorem to expand 2x squared plus 1 all cubed to get a whole heap of terms. And then you could expand by multiplying 4x through to each of those terms. That will give you a whole range of terms which you can then anti-differentiate them and then evaluate them on the interval. So you could do that, but wait, there's a shortcut, because if we have a look at the two things that are multiplied together, can you see that the internal part that we're cubing, 2x squared plus 1, when I find the derivative of it, I get 4x, which is what we've multiplied the expression by. So this, in fact, can be done by substitution. Okay, now I'll take you through it because I did go through it a couple of lessons ago, but it doesn't hurt for you to see it again. It's a 1, I believe. Can you have a look at example 12D for me? But I'm pretty sure it's 1. Thank you. So picky, this class. I don't know. Is that better? Okay. Is that what you mean?
Yeah.
Okay, cool.
Sounds like it's looked at the sun.
All right. Sorry, I'm just being a bit off task there. I'll just sort of make it a little bit bigger just for my own sake more than you. So the integral from 0 to 1, 2x squared plus 1, or cubed, times 4x, and we notice that the inside bit here is the derivative, or the derivative of the inside bit is given by the product there. So we do something like this. I'm going to go through it properly. I'm going to, hope I've got enough room. Let u equal 2x squared plus 1. Therefore, du by dx is equal to 4x. And I didn't do this when I went through the explanation with you last time, but I'm going to do it this time because it might really help people out, which means that that du is equal to 4x dot dx. Now, again, technically you can't really do that because dy by dx or du by dx is a concept. It's not actually a fraction, but it actually genuinely does work. So I've literally got an expression 4x dx, which is du. So that means that the integral of from 1 to 0 of 2x squared plus 1, all cubed, times 4x dot dx is actually equal to the integral of u cubed du. If color coding helps you, then there's some pretty colors for you as well. What do you reckon? What have I actually, I make mistakes all the time, but what have I deliberately not filled in yet? Oh, I'm glad I asked the question because it's some things stare at me like clearly I've missed this out, but if it isn't for you, that's okay. It means that it's a good place to stop. What haven't I filled in there on the after the equal sign that's present on the left-hand side? Ollie? You look like you wanted to say something? I've changed the dx to du because 4x dx was moved to du, so that's okay. It's now with respect to u. Is he? Yeah, I haven't put the endpoints on, have I? It was 0 to 1, but because we've substituted, it is no longer 0 to 1. Okay, so what do we do? I'll just do this in a box over here. The interval was 0 and 1, so when x equals 0, u equals 2 times 0 squared plus 1, which equals 1. And when x equals 1, u equals 2 times 1 squared plus 1, which equals 3. So the interval, so the new interval for u is 1 to 3. Is that okay? Might sound like a pain in the butt, but now that we've redefined it, the interval, we don't actually have to go back to that original function at all. We can now just derive with respect to u, and we're good to go. We don't need to resubstitute in. So good. So the next line is equals, anti-differentiate, so it's a quarter, u to the power of 4 between 3 and 1, which is a quarter times 3 to the power of 4, minus a quarter, 1 to the power of 4. I could have taken out a common factor there of a quarter, but my care factor was 0, so I just left it as it is. It's not too complicated, so I didn't bother. 3 to the power of 4 is what, 81? So I've got 81 over 4 minus 1 over 4. I'll do this in 2 steps, although you could do it in 1. That's 80 over 4. Do I have any more space? No, I don't. So I don't like putting equal signs. Knows my equal signs all go underneath each other, so I don't like doing what I'm about to do. Isn't it? 4, yeah, 20. So there you go. So notice that after the substitution step here, I never return to this horrible complicated expression. Don't need to. So I didn't get to this point and then substitute in. I don't need to because I've already changed the interval. So good. So with the new interval, I just evaluate from that point on, and therefore what I've got there, 20, is the solution for this horrible looking integral here. So again, the moral of the story is this: try and work smart, not hard. Okay? The hard way of doing it would have been to expand it and expand it again and then integrate all the parts and substitute. I promise you, if you did that, you would get the correct answer. You would get 20. You would also lose about 3 pages of your book, not really that long, and maybe 10 minutes of your life. Okay? Whereas working smart, where you look at methods like substitution, right? Or that sort of like you were pointing out before, the linear thing where the in effect internal function is linear, then using those tools in order to quickly anti-differentiate can save you heaps of time. All right, on page 311, you'll see example 12A, B, and C, as well as D. I'm not too sure whether they did it the same way as I did, but would have been roughly the same. So you've got more examples to look at. But yeah, these harder ones are now in exercise 9J. Now, if you're still feeling really like, I'm not really confident with these at all, please feel free to continue on with exercise 9I and build up your confidence. But know that in your own time, you're going to have to try some from 9J. You can't just stop your learning at 9I and say, I won't bother looking at 9J. But if you're feeling at least halfway confident, please have a go at exercise 9J because you're practicing the same skills as 9I, except with more complexity. So even if you slow down a bit as you attempt them, it's probably worth doing. But again, in 9J, you're looking for tools or patterns that you can use to solve the problem. Does anyone have any questions before I let you go?